Hello ladies and gents, this is the video for the practice IA number 3. There are 24 questions. A lot of these are going to be sort of repeated ideas from the previous work energy springs test we took like about a month ago. And the only thing new is electric charges and a little bit of the intro to electrostatics. Shouldn't be terribly difficult considering we've already tested ourselves on the previous old topics. And hopefully we'll be able to learn from mistakes from that old test moving forward to the IA. And let's go over some of these questions. And first off, I'm just going to move this to the side because I feel like some of these first 6 questions require a lot of space. Okay, there we go. So let's start with number 1. What is the kinetic energy of a 55 kilogram skier traveling at 9 meters per second? Also, I forgot my Apple Pen at school, so forgive the handwriting. I'm using a different stylus that is not quite as precise. Okay, so number 1, we're looking for the kinetic energy. Okay, they also gave us the mass of the person, 55 kilograms, and the person is traveling at a velocity of 9 meters per second. And we're looking for kinetic energy. This is our equation. Equals 1/2 mv squared. As you can see, my handwriting's terrible with the stylus. So when you calculate it all out, you should get an answer of 2,227.5 joules. So they all have these in scientific notation, so you move the decimal over to the left 3 times, and you should get 2.2 times 10 to the third as your answer, choice C. Okay, number 2, a 1 kilogram ball traveling east at 4 meters per second hits a wall and bounces back toward the west at 2 meters per second. Compared to the kinetic energy before, what is the kinetic energy of the ball after? Okay, so for number 2, we're comparing before and after. So my suggestion is to calculate for the kinetic energy before and after and then compare it. Okay, so before comes out to 8, after comes out to 2, and we're seeing how the after compares to the before. So 2, how does 2 compare to 8? It is 1/4 as great. If we were asking for the other way around, it would be 4 times as great. And I've seen a few of you make that mistake, so you got to read those questions carefully. Okay, number 3. A shopping cart slows as it moves along a level floor. So keyword, it's slowing down, and it's moving along a level floor. We're looking at kinetic and potential energy. How do they compare? So if the shopping cart is slowing down, we're thinking about kinetic energy because that relates to motion. So if it's slowing down, it's decreasing. So we're crossing out A and B. So that means we have to look at potential energy. We are on a level floor. We're not changing height. If we're not changing our height, that means gravitational potential energy stays the same. You need to look out for those key words. Remember all those mistakes you made on the previous test. A lot of you weren't reading the questions carefully for those words. I'm pretty sure if you saw those words, you would instantly know the answer. We just weren't reading carefully. Okay, number 4. As a bullet shot vertically upward rises, the kinetic energy of the bullet, so there's nothing to indicate that it's moving at a constant velocity, so we could cross out choice C. Now we have to think about if it's going up or going down. Alright, so if it's moving upward, think about throwing a ball upward. Because gravity acts downward, objects moving upward will slow down. Hence why it's going to A, decrease. Number 5. The gravitational potential energy with respect to Earth that is possessed by an object is dependent on the object's what? So, potential energy, we have to think about the equation. PE is equal to mgh. Okay? M is mass, G is acceleration due to gravity, and H is the height. So all of these is going to be position, okay? It's based on position most importantly. The only time G is ever affected is when you're on a different planet, but we're assuming everything on Earth. So with respect to Earth. So that means G will stay the same wherever you are. Okay. Now number 6. This is the big one I want to really focus on. I know I probably explained it to like all 3 of my classes, but I still want to go over this point. There's a question similar to this. A 1 kilogram rock is dropped from a cliff 90 meters high. After falling 20 meters, the kinetic energy of the rock is approximately what? Okay, So this is 90 meters. That's our starting point. Oh, where did the 0 go? Okay. And this is 0. Okay. So thinking about our energies at each of these points, remember that wherever we start with, that's where we're going to carry throughout the entire way. So at the top, we have max potential energy. And if you calculate it mgh, it comes out to about 900 joules. Now, that 900 joules you start out with at the top, you're going to carry that same total throughout. So by the time you reach the bottom where you're moving at your fastest, max kinetic energy, that will still be the same 900 joules, because think of conservation of energy. All your energy converts from one form to the other, stays constant, the total. So that's our total. Now, we're talking about moving downward 20 meters. So let's say it's approximately like right here. 20 meters later, we are at the 70 meter mark, correct? So we're neither at the top nor we're at the bottom. We're somewhere in the middle. We still have some potential energy because we're still at above the ground level, correct? We still have some height. We're 70 meters above the ground. So there's potential energy there. But we're also moving at this point because the rock was dropped, and we reached 70 meters. So because it's moving, we also have some kinetic energy. Keep in mind, anywhere in between 90 and 0, from the top and the bottom, anywhere in the middle, we have a mix of both energies. It's not going to be split 50-50 until we reach the halfway point. But once we're somewhere in the middle, we have a mix of them. Now, because we're at 70 meters, we're closer to 90. So you should think we're still really high above the ground, so we're going to have more potential energy. Okay, so let's cross out some answers already. We know that D is not the answer because that's our max at top and bottom. And then let's look at choice A. That's not even possible either. That's still too little. So let's look at either B or C. Okay, so at the 70 meter mark, we're going to calculate what's our potential energy. Okay, now keep in mind that our total energy will still stay 900 wherever we are. So let's calculate this. So PE is equal to mgh. If you notice at 90 meters, it approximates to 900. We could approximate this to 700 joules if you do mgh. So 1 times 9.81 times 70. This comes out to about 700 joules. So that means out of the one that is remaining, 900 minus 700, you have 200 left over for kinetic energy, and that's what our answer is. Choice B, 200 joules. Think about it. When you're closer to the top at 70 meters, you're going to have more potential energy. So between the two, 200 and 700, 700 seems more likely for the potential energy. That means 200 is left for kinetic. Now, as you flip it on the other side, let's say we're 20 meters above the ground. If you flip it around, this time we're only going to have 200 joules of potential energy and 700 of kinetic, because now we're closer to the ground. So think about where your position is, and think about if your answers check out to what you know theoretically. All right, now we're on numbers 7 through 12. Here, number 7, a 1 kilogram ball is dropped from the top of a building. Just before striking the ground, the ball's speed is 12 meters per second. What was the ball's gravitational potential energy relative to the ground at the instant it was dropped? So here we're calculating for potential energy, mgh. Well, looky here. I kind of rushed myself and assumed it was mgh. But look, we don't have height, and we need height to calculate for potential energy. However, they gave us something else. They gave us this. They gave us the speed of the ball right before it hits the bottom. Keep in mind, potential energy at the top equals kinetic energy at the bottom. So that's what we're looking for. We're looking for potential energy at the top. And keep in mind, this is also equal to kinetic energy at the bottom. So we could use this instead. Kinetic energy is equal to 1/2 mv squared. And you should get 72 joules as your kinetic energy at the bottom, which is equal to kinetic energy at the top. Okay. Choice C. Alright, number 8. When a mass is placed on a spring with a spring constant of 60 newtons per meter, the spring is compressed 0.707 meters. How much energy is stored in the spring? Okay, another mistake I saw, common mistake, is confusing the two equations. So for number 8, there are two types of spring equations. Fs equals Kx, that's for force in a spring, But most of what we're looking at is energy inside the spring, 1/2 kx squared. That's what we're going to use here. Okay, so 1/2, k is the spring constant, 60 newtons per meter. Okay. So I could see why you might be confused to use that Fs equation because the spring constant has a unit of newtons. So you're thinking force. But that's just spring constant. It applies to both equations. Next, we're going to use our compression distance, 0.707. Okay, don't forget to square it. That's a common mistake too. And you should get 15 joules as your answer, choice C. All right. Now, number 9. A horizontal force of 20 newtons. Oh my god, my handwriting's atrocious with this stylus. Causes a 10 kilogram box to have displacement of 2 meters eastward. The total work done is simply work equals force times distance. Alright, so that's just 20 times 2, and you should get 40 joules. Number 10. Let's pick a different color. 50 kilograms student runs up the staircase. Okay. Mass is 50 kilograms. Distance is 20 meters. Time is 7 seconds. We're looking for power. Power is equal to work over time. Force times, Yeah, DK, what just happened? Alright. Force times distance over time. Or force, oh my god. The stylus sucks. Sorry, guys. Force times velocity. Alright, so power is equal to force times distance over time. That's what we're using. Because they gave us distance, time, and we need to figure out our force. Now, if they give you the mass of something that's moving vertically, so you gotta keep in mind, if they give you a mass and you need a force, you gotta turn that into a weight by multiplying it by 9.81. So 50 kilograms times 9.81 times the distance of 20 over the time of 7 seconds. And you get about 1400 watts. So if you move the decimal 3 times over, you get 1.4 times 10 to the 3 watts. So that capital W might confuse for work, but capital W as a unit is watts. Capital W as a variable is work. Okay? And now we get to numbers 11 and 12, where we're thinking about electrostatics. A glass rod is given a positive charge by rubbing it with silk. Okay? The rod has become positive by losing electrons. Okay. So you just got to keep in mind that positive means less electrons, and being negative means more electrons. You only transfer electrons between objects. You never ever gain or lose protons in this scenario. So you're either gaining or losing electrons. So number 12 then, a particle could have a charge of what? So we got to keep in mind possible charges have to be multiples, whole number multiples of elementary charge, which is this number. 1.6 times 10 to the negative 19 coulombs. This is in the reference table, equal to E. Do not confuse it for electron. The electron is E to the negative, and then elementary charge is just E. Okay? So we're looking for whole number multiples. The easy way is to take, as long as they're the same exponent, and looking at each of our choices here, all of them have the same exponent as E. So we could just take their base number there, the first number, and just divide it by 1.6. And you got to look out for the whole number multiple. So if you look at choice A, 0.8 divided by 1.6 gets you 0.5. That's not a whole number. B, 1.2 divided by 1.6, that's about 0.75. That's not valid either. Choice C, 3.2 divided by 1.6 gets you 2. That's valid. Now look at D, 4.1 divided by 1.6. That's more than 2, but not quite enough. It's 2 and some decimal, so that's not valid either. So it's choice C, because it's the only one that comes out to a whole number multiple. Imagine a marble being an electron. It holds 1.6 times 10 to the negative 19. That's the smallest possible charge. You can only increase in increments of that electron. You can't have part of an electron, like 1.6 of an electron. Okay, so number 13 is a little bit of a tricky question too. So here we have a block weighing 40 newtons. That's already mg, by the way. From rest on an incline, 8 meters above. So we're at the top. So our potential energy up there is what we have as max energy to start with. So that's 40 for mg already, times our height of 8. You get approximately 320 joules to start with. And my handwriting is atrocious. I hate the stylus. I'm sorry for ranting, guys. But we're not done here. 320 joules is our max. They tell us that we took away 50 joules of heat because our incline has friction. So what does that mean for kinetic energy at the bottom? As you're going down, 320 joules is being converted. 50 of those joules is taken away to convert to heat because of friction. That means we have 270 left for kinetic energy. If you think about our conservation of energy lab with the marble rolling down the ruler, that's what's occurring there. You start with all that potential energy, and then you calculate it, and your kinetic energy is less. Why? Because you lost some of it to friction and sound, internal energy. Okay? And that's what happens here. Number 14. As a ball falls freely toward the earth, its kinetic energy increases because it's speeding up. 15. If the speed of a car is doubled, the kinetic energy of the car is... So we need to look at this equation right here. Ke equals 1/2 mv squared. So we're looking at speed, which is v. If you double it, imagine putting that 2 there. Okay. What do you do when you square that 2? You get a 4. So that becomes quadrupled. Now we look at number 16. A girl rides an elevator that moves upward at constant speed. So we're moving up at a constant speed. So if we're moving up, our gravitational potential energy is changing. We are increasing because we're moving upward, gaining height. And then our kinetic energy, keyword is constant speed, so it remains the same. Okay. Now number 17. As friction slows a cart moving along a horizontal surface, the gravitational potential energy of the cart... Okay, so we're slowing down, so kinetic energy decreases, but we're moving along a horizontal surface. So think about potential energy. If we're moving on a horizontal surface, we're not changing our height, so potential energy stays the same. Number 18. A spring stores 10 joules of elastic potential energy when it is compressed 0.2 meters. What is the spring constant? So we're using the potential energy in a spring equation, 1/2 kx squared. We're looking for k, and this is 10. So make sure you do your math appropriately. 20 equals 0.04 k. 20 divided by 0.04 will get you 500 newtons per meter, and that's our answer. All right, number 19, we're talking about an electroscope. So, keyword, the electroscope is neutral, so that means the electroscope, this contraption, has both positives and negatives. And here we're placing a negative rod near it. So let's look at each of our choices. So we already know that choices A and D are out because our electroscope should have both positives and negatives in it, as you can see in B and C. Now, all the rods here are negative, so we just need to see which one should be at the top. So because negatives are in the rod, that means whatever is opposite to that should be attracted to the top. Now, because opposites attract, the positives are going to be present inside the top knob, which means what's getting pushed down to the bottom leaves are the negatives. Okay. So the negative rod attracts the positive charges to the top and pushes away the negative charges to the bottom, hence why our answer is choice C. Number 20 is almost like a question on the previous page. A glass rod becomes positively charged when it is rubbed with silk. This net positive charge accumulates because the glass rod lost electrons. Again, when you become positive, you lose electrons. The more positive you become, the more you lose electrons. The more negative you become, the more electrons you gain. All right, number 21. A subatomic particle could have a charge of what? So, again, we got to look at our shortcut. If you look at choices A and B, that exponent indicates it's like a bigger negative exponent, so it's become an even more, it's going to be a more decimal kind of a number, so we can cross those off, because that number are smaller than 1.6 times 10 to the negative 19. Okay, the more negative that exponent is, the smaller that number. So we can cross off A and B because they're going to be smaller than this. We can't have that. Now, because C and D have the same exponent, we could easily do our shortcut. Take 3.2 divided by 1.6 and 5.0 divided by 1.6, and you'll get that choice C is the only possible charge of this group. 22 again is the same kind of idea. Which quantity is not possible? So this time we're looking for the decimal here. So if we could already cross off choice C because that's the same number we looked at 21. That's a possible charge. 8.0 divided by 1.6 gives you 5, so that's possible. B, 4.8 divided by 1.6 is 3, so that's a possible charge, which leaves us with choice D. 2.6 divided by 1.6 is 1 point something, so that's a little bit more than what we need. That's not a possible charge. Now, number 23 is dealing with conservation of charge. So here we're talking about two objects. One is a positive 2, the other one is 0. When two charged objects come together, their charges are going to mix together and divide separately. They're going to transfer charges until they reach equilibrium, which means both objects have the same charge. So the way we could go about finding out their new charges is to add up their charges, find their total, and then divide it up evenly. And so the total is positive 2, divided up evenly, and you get positive 1, positive 1. And that'll be choice A. Each sphere will have a charge of positive 1, because now equilibrium is reached. And then our final question here is another kind of conservation of charge question. Again, two spheres are separated at a certain distance. Now they're brought together. If they were touched and together and separated, what would be their new charge? So positive 2, negative 8 come together, and your total charge is a negative 6. Split them up evenly, and you get negative 3 and negative 3. Choice C. And voila, we're done. Hope you bore with me with my terrible handwriting and my angry rants about how terrible this stylus is. But nevertheless, you can go back and check out the Work Energy Springs topic review videos if you need help with those topics. If you need a little bit of extra help with the electric charges, I highly suggest you might have to poke around to last year's content review videos. I believe I have an electrostatics video up related to these topics. You might have to poke around to last year. But anyway, take care, guys. Hope this was helpful. I hope those of you from second period better show up first period for review. Take care, guys.